Well, good evening, everybody. Tonight, the webinar for the Deep Reinforcement Learning Nano degree is going to be on a kind of a new topic. We've been talking a lot in the past about action value methods, and today we start talking about policy methods. And so this will be an interesting lecture, I think. We'll start by reviewing some of the methods behind how you use a policy-based method to estimate the policy, and then use that policy network to directly generate actions from a given state. And then we'll apply that to a particular algorithm called reinforce, which is probably the simplest of the policy-based methods. And then from there, we'll talk about a application of the method on the OpenAI Gym's CartPole project. So with that, let's start with the slides here. Let me go into presentation mode, just a second. Okay, so this is the topic, reinforce in the CartPole project and an introduction to policy gradient methods. So as I mentioned, the objectives this evening are to introduce how policy gradient methods work, and then discuss a particular implementation of policy gradients called reinforce. It's a Monte Carlo policy gradient algorithm, and since it's Monte Carlo, we'll see that it requires you to actually do an entire episode in order to do the learning process, the training process. So it's not a temporal difference method that you can do step by step, but rather requires you to actually go through and complete an entire episode before you apply all the learning throughout. Now we'll walk through a sample of implementation of reinforce in the OpenAI Gym's CartPole mini project. So let's start with some general theory about gradient methods, policy gradient methods. Before we do that, though, probably should mention that up to this point in the course, most of the work that you've done and that we've talked about have been associated with action value methods. So it's worth probably reviewing what those are to contrast them with the policy gradient methods. So action value methods, they learn values of actions in particular states, and then once those values of those different actions are determined in a state, then the approach is to select the action when you're in a particular state that most optimizes the reward or the return for that particular state. They can work really well with discrete action spaces, but since you're really selecting a particular action based on those specific predetermined or calculated action values, they don't really work very well with continuous action spaces. So one thing we'll find out with these policy gradient methods are that they really do work well with the continuous action spaces. So if you have a problem where you have to choose continuous type actions rather than discrete actions, policy gradient methods is a way to go. The other thing is that action value methods, they sometimes or often have trouble with stochastic action policies. There's an example in the textbook 13.1 called a short corridor with switched actions. And in that particular example, it's a pretty simple example, but you basically have to try to get to a terminal state that gives a good reward. But whereas normally you go right when you select the right action in most of these states, in one of the states when you select right, the environment actually has you go left. And if you select left, it actually switches that and goes right. And you can look through that example and see how an action value method would have a very difficult time solving those types of problems. So with that quick overview of the action value methods, let's now talk about policy gradient methods. So in a policy gradient method, the approach is that you want to learn a parameterized policy. Now, what we mean by parameterized policy is that the policy is defined by some parameter. And we'll find out here in a second that the parameters that we use actually are the weights of a neural network, and all the combination of all the weights become that parameter theta that determines what policy is being employed. So you could think of, like an optimal policy in previous method might be to, in each particular state, select the optimal action from the calculated action values, if you're using one of those earlier methods. In this case, the policy is actually represented by those weights of a neural network. So given a state that you're in, those neural network weights determine the policy, and they're used to then, through a forward propagation, select an action from that input state in the parameterized policy. So a unique feature of these policy gradient methods is that they can select actions without consulting a value function. So you don't have to calculate value functions in the process of selecting actions. But you will also see that we will use those value functions in order to train the network. But once it's trained, it's no longer necessary to calculate value functions. The policies embedded in the weights of that neural network, and you just do a forward propagation step, and you get the action based on the state inputs. Another interesting advantage of policy gradient methods I mentioned earlier is that they work well with continuous action spaces. So we can see that the output actions that you would get in the final layer of a neural network can be continuous values, and so those actions that you select with this method also work well with those continuous action spaces. I'll also find that it actually could be easier to approximate a policy gradient or policy set of parameters than it is to approximate the action value functions that we have been using previously. And the final unique feature of these algorithms that's very advantageous is that these action probabilities change smoothly as a function of the learned parameters. So those learned parameters are the weights, as I said, of a neural network. We'll see in a second. And as those weights change smoothly in small increments, the actions also probabilities of actions also change. That's not really true in an action value method, because a slight change in a value would have perhaps a large change in the action that you would choose. So you see that a lot in discrete kind of action spaces in general. So as I mentioned, we might be calculating value functions. We will be calculating value functions while you're learning the policy parameters. But once you've learned those policy parameters, once the weights have been established in the policy function, then the value function is no longer needed. And as I've been referencing here for a bit, the parameters that we're talking about here in a deep reinforcement learning become the weights of a function approximating neural network. So again, we talked a few webinars back about the fact that neural networks are excellent universal function approximators, and here they're being used in the same way, and the function they're approximating is the policy function. So we use traditional gradient descent to train these types of networks, and it's the theory behind it is very strong, and it works very well in practice. A little aside here, this reinforcement algorithm we're going to talk about is the first introduction to a policy gradient algorithm. It's a very simple algorithm, we'll see. And in reality, in most real-world kind of problems, you probably don't use reinforce too much. Sometimes it's used as a baseline to compare other algorithms against. But you'll find in subsequent lectures and the final two projects of the course, you're probably going to end up using a state-of-the-art type of algorithm called an actor-critic algorithm, and there's many variations of these actor-critic algorithms. But in real problems, you'll be using those. And the actor-critic problems actually have two parts, an actor and a critic. And again, this is just a quick aside and introduction, but the actor part of it, it actually is a gradient, a policy gradient method. It learns the policy and selects based on the inputs in that learned policy parameters, it selects an action to take. So that's the actor. And then the critic is used as a traditional action value function, and it's used to sort of evaluate the actor and provide some feedback that helps improve the actions that you select. So those actor-critic algorithms, as I said, are more state-of-the-art, and those are the algorithms that you actually use. But it's good to understand a simple algorithm like the reinforce algorithm to get a better understanding of these actor-critics when you get to that point here in the course in the next week or two. Okay, I'm not going to go into too much detail on the policy gradient theorem but I will introduce it to you here. This is the statement of the theorem, the policy gradient theorem. There's a proof in the textbook. It's a single-page proof, and you can follow that along in section 13.2 of the textbook if you'd like to see the details of that. But I'd just like to talk a little bit about this theorem and explain sort of how it operates, and sort of intuitively how maybe it makes sense that this type of an approach would work. So the first thing is on the left side there is something called J. If you're used to developing a loss function for a neural network to do gradient descent on, this is sort of the opposite of a loss function. It's a performance function. So it's the inverse of a loss. In a traditional gradient descent, you'd want to minimize the loss. Here you want to maximize the performance. You want to maximize J. So this J function is a function of the parameters of the neural network, theta. Those are, as you'll see in a bit, for us in DeepRL, those theta values are just the weights of the universal function approximating neural network that we're using. So that performance function is proportional to a couple things, and the two things on the right that you see there are the proportionality values. Let's talk about the second half of that first of all. That second summation, as you can see, it's over all actions. So you sum over all actions. You weight the Q values that you get following that policy for a Q value in a state action pair by the gradient of the probability of taking that particular action when you're in the given state, and given the current policy parameters theta, which is again the weights of the neural network. Then, so that kind of makes sense. You're going to weight the values that you get by the probability of taking that action in that state. So that seems to make sense. And then the first summation then weights those results by how often each state occurs under the target policy. So that essentially is the policy gradient theorem, and we're now going to be applying that in this algorithm called reinforce. So the reinforce algorithm. This is, I mentioned earlier, as a Monte Carlo. I don't actually have that on the slide here, but it's a Monte Carlo technique. But we are going to update a particular state, a particular set of weights. Sorry, not on a state. A particular set of weights are going to be updated with this formula. So the new values for the weights is going to be the old values of the weights, plus this term on the right of the equation you see here. And there's 3 or 4 different parts of this equation. The first part is alpha. You can think of that as a traditional learning rate in a gradient descent type of learning neural network backpropagation learning method. You're going to take that learning rate times the total return, the total discounted return G, and that's going to be times the gradient of the probability of taking a particular action divided by the actual probability of taking that action. Now, the interesting thing about this is the third bullet I have here, and that is that the updates, as you can see, are proportional to the gradient, but they're inversely proportional to the probability of particular actions taken. And this has some kind of intuitive appeal because it prevents really frequently occurring actions from dominating the results, even if they don't provide the highest return. So dividing by that probability of occurrence kind of mitigates that particular feature, and then sort of optimizes the results for the actual returns that provide the best reward, best total reward. And remember the gradient, it's a vector whose direction and parameter space, which again, parameter space for us is the weights of the neural network, the space that is determined by those weights. The gradient is the direction in that space that most increases the probability of repeating a particular action on future visits to that same state that we're evaluating here. So as you can see, that's intuitively it seems to kind of make sense. It's a pretty simple update rule. With that update rule, let's just take a look here at the actual algorithm. And this is the Monte Carlo policy gradient algorithm as stated in our textbook. Should have put the page number or something on here, but if you look up the reinforced algorithm, you'll see this pseudocode for how it's implemented. As you can see, it's a pretty simple algorithm. You input basically a differentiable policy pi that determines a action given a state and the parameters of the neural network in this case. So it's going to do this policy says if you're in this state and we have this set of weights in the neural network, you can run through a forward propagation step and determine what the actions should be. Another input to this algorithm, as we mentioned on the previous slide, is the step size alpha. That's kind of the learning rate parameter. And the first thing you do is initialize all the policy parameters, theta, to some value. Sometimes this is set, all the weights will be set to 0. There's other research that's been shown to say that 0 is probably not perhaps the best value to use. And there's a lot of different research papers on how to choose a better value for theta. But in essence, you need to choose some value as the initialized values for all the weights of the neural network. Once you do that, then you basically go into a loop, and you go through this loop once for each episode. As I mentioned, it's a Monte Carlo technique, so we have to generate an entire episode, starting with state 0, taking action 0 in that state, returning from the environment a particular reward for taking that action in that state and a new state to transition to, and then repeating that until you get to the terminal state. And you do all of those actions following the current policy, which is specified by the current parameters, theta, the weights of the network. Then once you've generated that entire episode, then you start analyzing all of the values of those of that episode. First thing we need to do is go through and generate the total return, G, for this episode. And we do that, it's a discounted return, so you see gamma in the formula there. And you basically discount each of the rewards based on what step they were within the sequence. Then once you've determined the total return G, then we can go ahead and make that update to the parameter of theta, the weights of the neural network. And you basically replace the current values of theta with a new theta that starts with the old values, adds in that alpha value times gamma. Now, previous slide, we didn't really talk about gamma because it sort of simplified things by not doing a discounted total return. Here, we're actually doing a discounted return. So we have gamma to the t value. And again, gamma should be a value between 0 and 1. And so that discounts future rewards more than the more current instant rewards. Multiply that by the total return that we got, G, which we calculated in the step above. And then that's multiplied by the gradient of the log of the policy of actions that you took in a particular state, given that value of the current weights of the network data. So a pretty simple algorithm. It's repeated here on the slide, but I just wanted to mention a couple things. Remember that it is Monte Carlo, so it's a complete return from all time through the entire episode. It's good for episodic kind of tasks. It doesn't work as well in tasks that are not episodic. And all the updates to the network are made in retrospect. You have to wait till the entire episode completes. All the data is available. Store all that data into a set of data structures, and then once that's all done, then you can go ahead and make an update of the parameters, and then repeat the next episode and do the same process over again. Okay, so let's apply this reinforced algorithm to the CartPole mini project. This is a very standard project in all of reinforcement learning. Any algorithm that you might work with, a lot of times you might first apply it to a CartPole. It's sort of a baseline model for how you can compare different algorithms, and it's a very early implementation of reinforcement learning to learn how to balance this pole on a cart. So essentially, you got this pole. It's got a hinge where it attaches to a cart. and you try to balance this pole. You try to have an agent that learns how to balance this pole by taking a couple different actions, and the only actions available are pushing the cart to the right or pushing the cart to the left. And as you can see, as you push the, if the pole is starting to fall to the left, you would push the cart to the left, and it would help balance it. But then, if you overshoot, the pole will start to slide to the right, so you need to push the cart back to the right. And there's a window that you can't exceed, typically left and right, that you have to keep the cart also positioned someplace between those bounds. So the states are very simple. There's a 4-state set of values that define the state of this closed system. The first one is just the position of the cart itself and how fast the cart's moving. That includes a direction component. And then the last two are related to the pole itself. One is the pole angle from the horizontal, and then the velocity of the tip. So, if the pole is falling fast, the velocity of the tip will be fast. If you got it pretty well balanced, the velocity of the tip will be near zero. So the goal is really hopefully to have the agent learn how to balance that pole with zero velocity at the tip and make very small adjustments to keep it balanced there. So given those inputs, we want to input those states and then teach a neural network a policy that it can use to select actions based on those inputs. Pretty simple. So I'll mention here, it's worthwhile when you come across these types of problems to take a look at some of the documentation on PyTorch. This is a page out of the PyTorch documentation. You can see the URL there. One of the things that's used, as we'll see here in a second, I think I included this I didn't include the entire code, but I think I included the reference to a function in PyTorch called distributions. Sorry, not a function, a library called distributions, and it's got a family of algorithms within that library. One of them is called categorical, and those categorical functions are very useful. And in fact, when it introduces these categorical functions in the PyTorch documentation, it actually uses reinforce as an example, and you can see the definition of how this is determined, and then a really short 5 or 6 line implementation of reinforce. And we'll see the version we're going to implement is very similar to this. It's a little bit more detailed, but basically it follows the same structure. And again, it's worth reading this documentation when you're trying to learn about these algorithms. It can give some insight into how they work. So let's just do a quick walkthrough of the algorithm. I've got basically 2 slides here. This first one actually shows the policy class. You'll see in you've already already seen in some of the probably the first navigation project that you did. Typically, the way these algorithms are all implemented, there's 2 classes that are used, employed, and then a main program or a main Jupyter notebook that instantiates these 2 classes and actually uses them to implement an algorithm. And those 2 classes typically are a model class that would define the neural network model, and that's what this policy library that you see here, this policy class is. The second one is usually an agent class that actually implements the agent code. But here, let's take a look at if policy as an example of a neural network model. It's a very simple model. As you can see, it has an input layer. As we saw, there's 4 values that make up that state. The values that we talked about earlier with the position of the cart, the velocity of the cart, the angle of the pole, and the velocity of the tip of the pole. So those are the input states, and your only 2 actions to choose from are move left and right. So the inputs are those 4 neurons, and then the outputs are those 2 neurons that define the actions to take. And in between is a simple, very small 16-node hidden layer. It's very, very simple network. As you can see, the forward step just basically inputs the states, performs a fully connected layer to the hidden layer, and then does a simple ReLU activation function, and then outputs the value from that as a softmax function. So again, if you remember from your neural network classes, softmax basically tells you a probability of which distribution for the actions, the outputs in this case, which are our actions, and those probabilities will add up to 1. So if stochastically the actions are equally probable, they would both be 0.5. If one of them is 90% more likely to should be picked, then it'll be a 0.9, while the other action will be 0.1. It'll always add up to 1. And then the act function. Act function usually is actually implemented in an agent class. In this particular implementation of reinforce, they didn't include an agent class, so they've included this act function as part of the policy. Essentially, it inputs the state, taking those values that were just input as a NumPy array, converts them into a PyTorch tensor. That's what the first line does. And then it calculates the probabilities by doing just a forward pass through the network. And then this categorical, that's the function I was telling you about as part of the distributions package in PyTorch. M is a categorical class, so you define that based on the probabilities that you got. And then the action is just a sample from that class. And it samples from that class based on those probabilities, so that actions that have a 90% chance of probability would be picked 90% of the time, and those with 0.1 would be picked 10% of the time. And then the function act just returns the selected action along with that log probability value for the action, and that log probability is going to be used as part of the training. So that was the policy network. That's the neural network part of this algorithm. The next part is the actual implementation of reinforce. You can see the very first line. And again, this is not the entire algorithm. It's a snapshot of the middle of the algorithm. I kind of pulled out the most important parts here. At the top, you can see we instantiate one of those neural networks, and we just call it policy. We set up an optimizer, in this case an atom optimizer. It's a very commonly used optimizer for training neural networks. And then we define the reinforcement algorithm with the number of episodes that we want to run through, and the max number of mini steps within an episode, the gamma discount factor, and then define a couple of variables here for storing some intermediate data, a deck of scores, and the actual list of scores. And then we go through this loop. And this loop basically loops over all the episodes. So since we defined the default, if you call this with the default of 1,000 episodes, it would go through this loop 1,000 times. And it initializes some variables for the saved values of those log probabilities that we just saw come back from the act function. It initializes a set of rewards. These are the rewards for every step of the episode. So we'll be saving all those. And remember, since this is Monte Carlo, we have to save every episode from each state transition. So each step of the episode, we need to know what those rewards were. And then this state basically is just telling the environment to reset back to the beginning for a new episode. Then we go through a second inner loop of the max T mini steps. And for each of these mini steps, this is what defines all the different state transitions for one episode. We get the actions and the log probabilities from the policy network. Remember, the policy.act does a forward propagation through the network and provides those actions. And then we save those log probabilities in that deck that we saw defined earlier. And then tell the environment to take a step using that action that was determined from the policy. So it takes a step to the next state and returns to us the next state and the new reward for that transition. And so we save that reward away. If we ever get a done flag, which means we got to the terminal state, then we are done with this inner loop. And we keep going through that, either the maximum number of mini steps, in this case 1,000, or when we get to the terminal state. And that defines the end of the episode. So once the episode is over, we have all that data collected up with the rewards we've achieved, the log probabilities, the actions that were taken. All that information is available to us in those data structures. So we start here to implement the inner part of reinforce. We append the total value of all the rewards that we've got to the scores, and likewise to the scores deck, and also to the total scores list. And then we calculate the discount factors, which is basically the discount. This is an array of all the gammas raised to the power of I to get the discount rate for every step of the episode. And then calculate the total return, which is basically the sum of all the discounts, the discounted rewards. And that just that little Python A times B for A, B, and zip of discounts and rewards that basically runs through that entire set of lists of discounts and rewards, applies that A times B to discount each of those rewards to actually get you a total reward R. So now we go into the part where we're going to start getting ready to calculate the learning step for the policy network. So we first go through all the log probabilities and append those to the policy loss list, and that policy loss list then is used as part of the training, as we'll see here in a second. We first zero out the gradients of the optimizer. So we start with no gradients. We do a backward propagation step, which then propagates all the errors back through the network and uses that policy step as the optimizer to actually perform the back propagation. And that represents one step of learning. Once the weights are all been adjusted, we go back through and do the next episode. So that's all repeated as many times as you have episodes. So a fairly simple process. I should mention there's a mini project in the course. It has a notebook already programmed for you. You should go into that CartPole project and actually execute each of the cells in that notebook and watch the network get trained, and then watch it actually perform with the environment, learn how to solve that environment, and watch the agent, the trained agent, when you're done, actually move the cart to keep that pole balanced. It's a very simple 4 or 5 different cells. Most of them I've already talked about here. Just execute each one of them, and it doesn't take very long, maybe a minute or less, to actually train that network. It's very efficient. Takes a few hundred episodes, and it comes up with a policy that can balance that pole. So pretty impressive. So in summary, this evening we've discussed introduced really policy gradients. This is the first introduction to policy gradients, and we talked about how policy gradients, the theory behind them, how they work, and then we applied them in this reinforce algorithm, which again is a Monte Carlo policy gradient algorithm. So it requires us to actually go through the entire episode before we can make updates to the policy. And then we walk through an implementation of reinforce in the OpenAI Gym CartPole project. So with that, if anyone has any questions about tonight's topic, I have an Ask Me Anything session immediately following here. It's on Slack, so if you'd like to tune in there, ask any questions, be happy to answer them live. And with that, that ends tonight's webinar, and we'll see you next week.